Hi, so we're very happy to have Tomasz Kaczynski from the University of Sherbrooke, who's going to talk to us about computational homology, dynamics, and data. And he'll give us like Benjamin, he'll give us a 3-lecture mini course. Tomasz is one of the people who's been working for a long time in things that we now call applied topology. So we're very happy to have him with us. So thanks.
Thank you for introduction. Do you hear me well?
Yes.
Yes.
Very well.
Hello. Buenos dias. I will start my talk. So my talk is mostly all my 3 lectures. The set of 3 lectures is an overview and not very new things for you. Many things were done something like 20 years ago. So here there is, I have a little problem with using, okay, now it works. So I start with overview of applications, but there are too many applications to overview, so I will be focusing on extracting features from images and chaotic dynamics. I realize that what would be of your greatest interest would be persistence, but that would be a separate lecture 3. After that overview, I will do briefly homology, the concepts. Then I would give the basic definitions related to a simplicial complex and its homology. Then I assume that most of people know that. I would spend more time on cubical homology, which is maybe less known. The appendix here, homology of a map, is something I might not have time to do in my lectures. But I noticed that you had the one of the first talk. I think Ioanni Reani. He spoke about homology of maps, so it might be useful to hear that if I have time. If not, I will maybe leave my slides. I think most of people here are topologists or applied topologists, so you all should know that topology is a geometry of position. So we study objects focused on properties which are invariant under continuous deformation. I am most interested primarily in algebraic topology, and here is a formula which everybody knows, I think, Euler formula, which has been known for like 200 years. If S is a surface of a convex polyhedron, and then this is what called Euler-Poincaré characteristics of a surface. Number of vertices minus number of edges plus number of faces is equal to 2. That's Euler formula. And to start, since these are lectures and not research talks, I start from an exercise. How many pentagons and hexagons are on a football or soccer ball, depending on where do you come from. You call it soccer or football ball. Next, so we have homology functors. So homology functor takes geometric objects and assigns to them algebraic structures. So from continuum information, we extract finite information. To make it more simple, we may consider scalars in a field. That is also good for computation. then the homology, we don't speak about homology groups or models, but about vector spaces. And the kth homology space of X is isomorphic to a certain power of the field. So then the beta k, the dimension of that space is the kth Betti number of X. Geometric interpretation, beta 0 is number of connected components, beta 1 generic loops, beta 2 cavities. So we think about holes in a Swiss cheese. We have a relation of homology to the Euler Poincaré characteristics. This is which is can be expressed as the sum, alternated sum of the Betti numbers. Now, a question one can answer using homology is this one: how many regions are enclosed in this maze or labyrinth? So what you see here is an image, and one can compute homology out of that image, of this image, without any interpolation. It is the image itself. There are black pixels which can be interpreted as squares. So we already have a geometric structure, and those squares are a part of can form a cubical complex. So without any interpolation, we can take the image, the pixel image, and put it into the program to compute the homology of it. We can play it, modify using a paint application and get different results. We have medical imaging. So we have a 2D slice of a brain. And so we can extract information from it by using an appropriate thresholding. And again, we have black and white pixels, and we can and transfer it into a topological information. Another example comes from material science. We have alloy microstructures. So that also can be expressed by as a 3D pixel image, and we can put it into the program which and count the Betti numbers. So there is one connected component, 1700 tunnels, and there are no enclosed cavities. Maybe I should mention that those homology programs I referred to, they are in CHOM-P. This is a computational homology project, which is now located at the Rutgers University. But that has been initially collaboration between me, Marian Mrozek, and Konstantin Mishaykov on the book Computational Homology, and also there was also led to the creation of the library of the programs. Another type of applications are related already to persistence. So sign alphabet signs. So we have those hand signs which with each gesture representing a letter of an alphabet. We extract the information in the photographies into contours. So these are different shapes. They are all topologically equivalent. So all of them are homomorphic to the black. The black contours are homomorphic to a circle. So one can ask, where is topology here? Well, we'll see it by using sub-level functions that we can distinguish between them by means of filtrations. 3D shape comparison, that is, that's another, I think that my reference acknowledgement have disappeared, but this is a courtesy of Claudia Landi. We have you have probably seen persistence diagrams in other talks. They could. This is a homological information of sub-level sets, which can be encoded and used to distinguish to judge the similarity or dissimilarity of 3D shapes. 3D shapes are 3D meshes obtained from scanning. Image morphology. So image understanding and segmentation is based on identification of isolines, contour lines, ridge ravine lines, watersheds. So that is used based on critical points, summits, pits, and saddles, which are important points of an image. Image is a function on a grid, yes. So these are important points of the image where for example, in saddles, isolines cross. In the image, we usually do not have any smoothness, so it's natural to immediately talk about topological critical points. I will give here a definition. First, we have a function with values in R, so it can be, for example, the gray level of an image for each pixel. The variables are pixels. So C is an essential critical value if the topology of the sublevel set given by this formula changes as the parameter A here passes through the value C. Now, what does it mean that topology changes? So there is a homotopy criterion that if we take the lower sub-image, X for the value C minus epsilon 1, then this is not a deformation retract of X with the value C plus epsilon 1. So that is a subset of that. We don't want, so if we can find sufficiently small epsilons such that this is not a deformation retract, then we would call it an essential critical value. And regular value is the one where for any epsilons, this is a deformation retract. There is a homology criterion, is a bit narrower. We look at inclusion of a smaller sublevel set into a bigger sublevel set. And we look at the linear map, which is induced in homology by that inclusion. Then if this map is, so we want, if C is a homological critical value, if that is not an isomorphism for some epsilons sufficiently close to C, small. That topic will be seen again when we talk about persistence. 2D experimentation, we have here again, you have seen this photography among the sign alphabet images, photographies. So we can analyze by using the digital image and create find saddles. So there are minima, saddle points, and local maxima, And using connections between critical points, we construct Morse connection graph. So the edges here display connections between critical components. That means these are not actually paths which join the critical components, but there is an edge if there is a connection. You will see this in lecture 2. Now, the other application, which is a bit more far away from the interest of this community, is the dynamics, in particular chaotic dynamics. So we have this famous Lorentz systems, where here this is a picture which you see often in books on dynamical systems. There is some kind of strange chaotic behavior here, with those loops being circled in arbitrary iterates, switching from one to another in various ways. The way to study that problem is to reduce the problem to the problem of studying a map, fixed points or periodic points of a map. So we have a Poincaré section, which crosses our a hyperplane, which crosses our loops, which we observed. And we have a Poincaré map, which, given a point in the Poincaré section, we register where does it, what is the first point at which a trajectory goes back to that section. So this is Poincaré map is also called first return time map. So if we have capital P, the Poincaré map, then there is a fixed point of the Poincaré map, P of x equals x. That is also a periodic trajectory, which goes back to the same point. So periodic point is pk of x equals x. That these are also this gives also periodic trajectories for the original system. So what does homology topology do with this? So this is F, but because it doesn't have to be Poincaré map, it can be any application. So F from X to X is a continuous map. We can compute homology maps for F. HK of F is a map induced in homology by kth homology by F. We take the trace of that. The sum of the diagonal entries actually, yeah, the trace and we of the ranks, and we compute the traces and the alternating sum. If that thing is different than 0, then F has a fixed point. If we compute Lefschetz map for Fk, we get a k periodic point. So that's just a brief idea on where homology is used for dynamics. Then we go to a brief overview of homology. You have seen homology in the talks before, even yesterday. So I think that most of you already have seen that topic. So the brief idea is that we have to do some kind of complexes. Sorry. Complexes permit registering connections between of interest between data points. So they can be vertices, sometimes called nodes, edges or faces. So we can, what kind of connections can be of interest? So you will see in the persistence, you have seen it already in persistence talk, but also in my lecture 3, proximity based. It's Edelsbrunner's alpha shapes. So we have those little circles here are nodes. We encircle nodes by disks or balls of certain diameter, and we look at the intersections and we build a complex from those intersections. So we have when we limit the balls to so-called alpha shapes. I will talk about this more in detail in lecture 3. So when two balls intersect, then we draw an edge between connecting the two nodes. If 3 balls intersect, then we have a triangle. So then we have we get a simplicial complex out of it. There is I like a lot Robert Grist's example of motivating complexes, which are, I think it appeals even to people who are not in mathematics. So we have, so we want to choose a meal, and we have a dilemma for choosing between fast, cheap, and reliable. So if we agree that we can make a compromise between cheap and fast, then we have an edge. A compromise between having at the same time fast and reliable, another edge and another edge. If all 3 are possible, then we would have a triangle. Now there is the same similar example but in 3D, a tetrahedron. So we have we want also the meal to be healthy, and now can we have the meal at the same time fast, cheap, tasty, and healthy? So if yes, then we have a tetrahedron. If only 3 of them, we would have a surface of tetrahedron which consists of 2 triangles, and so on. The homology idea is, so here at the beginning, this is like homology for people who know the graph theory. If you know the graph theory, then you know that connected as acyclic graphs, for a connected as acyclic graph, we have number of edges is equal to number of nodes minus 1. If we look at this graph, that blue part, or ignore green, then you can count that's exact. If we add cycles, what does happen? If we add a cycle, green cycle, then we have 1 more edge, but we didn't add any vertices. So if we take that formula, all this on one side, that would be 0 for acyclic graphs. Now cycles, number of cycles would be this, which is a beta 1. That is exactly the first first Betty number. Now look at this triangle. So this polyhedron. So what you see in yellow is there. The white triangle is absent. So you have a cycle which goes, which is this whole thing here. This is our Z1. We have another cycle, which is this contour of a triangle. So if we look at the 3 triangles, then their boundary, this is a 2-chain, will be expressed as a 2-chain, is the difference between the 2 cycles, algebraic difference between the 2 cycles. So we would call them homologous cycles if they are a boundary of something. So we build a vector space. For Z coefficients, there would be it would be a group or module, abelian group. vector space generated by k simplices of our k. So delta k from ck to ck minus 1 is the border relation, or the boundary map. So homology is the quotient space of cycles divided by borders. Cycles can be expressed as the kernels of the maps and borders as images of delta k plus 1. That's a different notation. So beta k, the Betti number in dimension k, it would be dimension of hk. This nice picture is again from Edelsbrunner book, and which shows the relation between the whole space of chains, cycles, and boundaries. They are contained within each other, and we have a relation where the things are mapped. The fact that we can those maps can be expressed as is in these pictures are related to the fact that the double boundary is 0. If we apply the boundary twice, then we get 0. So now we get into the simplicial complex definition. Geometric we have geometric and abstract. Geometric and abstract. So geometric simplex is a convex whole of a finite set of affinely independent vertices. So affinely means also called geometrically independent vertices. So if the phase relation between simplices means that the vertices of one simplex are contained in the set of vertices of the other one. A geometric simplicial complex is just the set of all simplices, not all simplices, some set of simplices with the properties that if sigma is in it and gamma is a phase, then gamma is in it. If there are 2 sigma 1 sigma 2 in it, then the intersection is either empty or a common phase of 2. So when you look at those figures here, this shows these are different. The first 2 are different triangulations of a square. So the triangles are there. The second one is not a triangulation. That does not represent a simplicial complex, because if we do look at this diagonal, it's not a common phase of that and this triangle. So we have a problem here. We have the theorem saying that any finite abstract simplicial complex admits a geometric realization in this space of an appropriately high dimension. For dimension n, we need just 2n plus 1. Now, what is a simplicial chain complex? One of the oldest definitions is mod 2, not for z, but for z2 coefficients. So if we have a simplex of dimension k and a gamma in k minus 1, then this incidence number is just 1 if gamma is phase, proper phase of sigma, and 0 otherwise. So it's just recognizing if this is a phase or not. There is no orientation involved. So simplicial chain complex is just the vector space over Z2 generated by SK, which are k-dimensional simplices, and delta k is a boundary map. How is it defined? Very simple. Delta k is the sum of the incidence numbers times gamma. And one can show that double boundary, the boundary operator applied twice is 0. If we want now to take account of orientation, 2 equivalence classes, we need to introduce equivalence classes of oriented simplices. So we write an ordered list of vertices, and they are equivalent if the two lists are equivalent if the permutation to get one from another is even. So we have we consider a free abelian group generated by oriented simplices. Actually, there is a little twist to it, but I will not stop here. And the boundary map is defined as alternating sum of a list with one vertex removed on ith place. So we have a k minus 1 phase. That's all. I will not spend more time on that because that's enough. Now I want to go to the last topic, the cubical complex. So we have cubical grids. What is the motivation for them? We have image data. So in image, we have pixels which can be interpreted as cubes. If we want to have a simplicial complex, we need to extract nodes, do interpolation, we have a smooth math model, triangulation, then we get combinatorial model homology. What we want to make a shortcut without triangulations. Also, so pixels can be interpreted as cubes, even if we see this image where we have two smooth circles, which seem to be smooth. If they are images, then this little thing would look like that. So we can interpret pixels as cube, and that gives immediately a cubical complex. There is a mathematical motivation for using cubical complexes, that simplex cross simplex, Cartesian product of two simplices, that is not necessarily a simplex. Usually it is not. But the one product of two cubes is a cube. We have homology calculus. So we have old problems, but there are new ways to more efficient to compute. So we need to compute the homology of spaces, but also the homology of maps. So as I said, I might have no time to do the last part of the slides about maps, but the basic idea is that in traditional approach for computing homology of maps, we need to do matrix algebra, triangulations, so matrix algebra. In our approach, we have cubical grid and we have elementary reductions. Now, when we have a continuous map, we have to refine subdivisions. So we have to have barycentric subdivisions and simplicial approximations. Here we do rescaling and multi-valued enclosure. If you need to stop me, please do so. We have cubical sets and complexes. We have what is a cubical set? Cubical set is a finite union of elementary cube. An elementary cube is an object in RD, in the Euclidean space. So it's a product of intervals, which are with all intervals have integer coordinates. And either it's a unit length interval or a node, the degenerate interval. Full cubes are the products of unit length intervals. They are pixels are full cubes. So the faces of cubes are distinguished in algebra, but not in the image. A cubical complex is built of the same way as the chain complex for a simplicial complex. So we get Ck of x is the 3 abelian group generated by elementary cubes of dimension k. So its elements are formal sums are called chains. The scalars can be in Z, or we can assume field coefficients R or Z2. So the cubical complex is the collection of those spaces or groups, 3 abelian groups, with boundary maps. Now, how boundary maps are defined? So the idea is in this picture. This picture sits in a plane. So these are coordinates of the vertices. There are so for example, this edge formally it's an elementary cube of dimension 1, which consists of a interval L plus 1 times the singleton k, and so on. All elementary cubes they do not carry orientation. So these all A2, B1, B2, A1 are just elementary cubes, geometric objects, no orientation. When we draw an edge this way, then we mean that we take in our chain with a sign plus. Where we draw an edge this way, then it means that we want to count it with a sign minus in front. All A's and B's are geometric objects with by default the same orientation as coordinate axis. So for that thing here, if I count the boundary map of Q, capital Q, it is here, then it would be A2 plus B1 minus B2 minus A1. That's an idea. Now, how do we get about defining that in a precise way? So we define it via a cubical product. Actually, cubical product, it is a tensor product. It's just that when we lecture, we don't want to make it too algebraic and scare people with the name tensor. So we have two chains, and the product, cubical product of those two chains would be the sum of Cartesian products of the elementary cubes with those products of the coefficients. So here is an example. We have, this is a square in R2, the boundary of a square. So we have 4 elementary cubes of dimension 1. This is in R. There are 2 elementary cubes of dimension 1, minus 1, 0, 0, 1. So if we take C1 cubical product C2, then we get this object. If we have C reverse, it's this object. So it's isomorphic, but it's not the same object. So now, how do we define cubical boundary map? We take our cubical set in RD. So small d is a dimension of the space. The cubical boundary map, delta k, would be defined on induction of d, not of k, but on d. If d equals 1, we have 2 cases. So we have a non-degenerate interval, L plus 1, then it's natural. It's L plus 1 minus L. And if I is degenerate, then it's I minus I, which is 0. Now we take a bigger dimension, d greater than 1. So we decompose Q as a product of an interval which is in R by an interval which is in RD minus 1. But that interval in R can be either of dimension 1 or 0. So delta Q is the boundary of I times P plus minus 1 to the dimension of I Q product delta P. So we get that theorem, which is in our book, that double boundary map is 0. So this is what we want from a boundary map to satisfy. Do you have any questions about that? We have, now we can define homology of a cubical set. We have, that is part is similar as for other settings like simplicial setting. So we have cycles. These are for whom the boundary is 0. Boundaries are chains for which are boundaries of some other cycles. Two cycles are homologous if their difference is a boundary. Homology equivalence is homology is equivalence relation. So we have group of cycles or space of cycles, boundaries. Delta square equals 0 implies that BK is a subgroup of ZK. Also, Z2 homologous to Z1 can be written as Z2 belongs to this translation of this subspace by Z1. Now, homology group is again the quotient group, cycles divided by boundaries. I will, in my other talk 2 at least, I would need to the notion of a relative homology. That is to define it. It's quite simple. To compute it is maybe not so simple. We have relative homology of a we have a cubical subset of B. Is there any question or something? No, I don't think so. I haven't. A is a cubical subset of X. So we have CK of X relatively A is CK of X divided. It's a quotient of two spaces or two abelian groups divided by CK of A. We can prove that there is a well-defined boundary map. Which is relativization of the delta K to A. We have ZK of the kernels are relative cycles. The boundaries, the images are relative boundaries. So these are cycles, relative cycles, are equivalence classes of chains of X whose boundaries are in A. And relative boundaries are equivalence classes of chains, which once completed by a chain in A, they bound a chain of X. We have a homology of X relatively A would be that quotient. Relative cycles by relative boundaries. We have interpretation. So what is so we have that we know that H0 shows us number of connected components, but here relatively A, that means number of connected components of X disjoint with A. Then H1 H1 of a space would be cycled, would be closed paths represented by closed paths, but here it's not necessarily closed paths. We have generic paths in X whose endpoints are in A. H2, there is a mistake here. There should be A. Generic caps in X with a rim in A. Okay, so this is an example here. We have this like horseshoe thing. X, capital X is the blue plus red set, both. It's the union. The red is A. So when we compute homology of that, we realize that it's isomorphic to computing H1 of that set, which is more simpler, which is homomorphic to a circle, relatively a point. And that is Z. I speak about H1 here. Okay, so these were relative homology. Now, computation. I want to ask you, Antonio, when should I finish?
About 1:10, I think.
1:10. Okay, I think I will be.
And even you have a little bit of leeway as well.
Yep. I started a couple of minutes later, but it's okay. I'm fine. So now about efficient computation. Many of you must have heard about elementary collapses. We have the so I will describe a method which starts from which is a generalization of elementary collapses. So we have a pair of elementary cubes Q in dimension m, m-1. P is of m-1. So it is P is a proper subface face of Q. So it's a pair of reduction if Q is the only cube which have P as a proper face. So if that's for elementary collapses, if P is then P is a free face of X. So the idea of elementary collapses is that by removing pairs for reduction, we reduce the size of the complex and the homology is the same. So the homology is the same. The problem is that there may be no free faces. So in this picture here, you see this full cube P, which is face Q. It's actually reverse in the picture, but I hope you will excuse me. Then we remove that edge and the whole cube, and we are left with those three edges. We remove that and vertex and that interval, and we are left with those two edges. Then we remove this point and this edge, and we are left with that. We could complete that construction, remove that. I should. Remove edge and vertex here to at the end to have a point. We have so we generalize elementary collapses to elementary reductions. Elementary reductions are somewhat equivalent in a sense to the Gaussian reductions, but they are on geometric level. And also, each time we do reduction, we diminish the number of generators by 2. So we reduce the size of the chain complex. So here, this is illustrated. We have the contour of the triangle. So the full triangle is not there. We have 3 vertices, capital ABC, 3 edges, small ABC. We take B and we redefine the boundary of B. We declare that now initially B, the boundary of B would be, for instance, C minus C, capital C minus capital B, but we declare that there is a new boundary which is obtained by carrying capital C to A. So then this is our B, and that's its new boundary is capital A minus capital B. Then here we redefine the boundary of A by looking at the vertex capital B. So we carry to A that way, and what we get, just the edge A and the vertex capital A. So that's an example of elementary reduction. What you see a sequence of 2 elementary reductions. So there is a theorem on it, which is quite old. It's 1998, due to Mrozek, Ślusarek, and me, that we have this sequence we can have sequence of elementary reductions which stops at the point where actually the incidence numbers, we cannot find non-invertible incidence numbers. And then the homology of the initial complex is the same as the homology of the final complex. And if the final complex have all boundary maps 0, then the homology of the final complex is just the complex itself. The homology groups are equal or isomorphic to the homology of the complex. Now there is a question related to here, is that the question is that this is not a simplicial complex, this is not a cubical complex, nor is this. So what meaning can we give to those structures? We can have here, so algebraic is now called as Lefschetz complex. So that's retaining pure algebra, and I would this is due to Lefschetz at the beginning of the 20th century, and geometric is the CW complex, which is so the geometric meaning is CW complex, that or cellular complex. Now I am practically done with what I wanted to do. But that's the appendix now. Computing homology of a map. I think, yeah, that might be a little bit too much, but I think I still have a couple of minutes of time. What is the motivation for computing homology of maps? So the classical example is that we take a circle and we take a continuous map from a circle to itself. So the homology of a circle is isomorphic to Z if we take Z coefficients. Then since any linear map in Z has to be on a number n has to be k times n, then the homology of that map, if it's well defined, it should be on the n, we should have k times n. So k is called winding number. So that represents how many, or wrapping number, how many times a circle is wrapped around itself, and which way. It can be negative. That's a classical motivation, and that is related to the terminology winding or wrapping numbers from complex analysis. So now we have cubical sets. We will try to go to the definition of the homology map. So continuous map F on cubical sets is cube to cube map if it is restricted to and if f of q is an elementary cube for an elementary cube q. So that's an analogy, cubical analogy of a simplicial vertex map. So there are some nice, some simple things. On elementary cubes, we can have permutation of coordinates and addition of coordinates, translation, and so on. And this is also inversion. So we can prove that a restriction of cube to cube map on any two elementary cube is the composition of these 5 types of maps. So a consequence is that if we have a cube to cube map, then we can give explicit formula for a map on a chain complex, right? Without subdivisions, anything, we can write down the map of a chain complex that it induces F star is the map induced in homology. We have a classic, a combinatorial version of a classical Vietoris theorem, which says that if we have a cubical cube-to-cube map, which is surjective and inverse image of each elementary cube is acyclic, then the map induced in homology is an isomorphism. So how do we use it? I will, in talk my lecture 2, I will be talking more about multi-valued maps. You will hear more about that. So we have a multi-valued map, which sends elementary cubes to sets of elementary cubes. And we say that it's an acyclic cubical enclosure of X if it has this following property. The graph is of small f is contained in the graph of the multi-valued map. The projections P from the graph to the x-axis and from the graph to the y-axis are cube-to-cube maps. And for the projections from the graph to x-axis, P minus 1 of Q is acyclic for each Q. So the consequence of Vietoris, combinatorial Vietoris theorem, is that we can take this inverse and we can define F star is the inverse of the map induced in homology by P composed with this one. And we can define the homology map of small f via that. So in the picture, one shows that our capital F is a kind of approximation, but in terms of graph enclosure of a continuous map, but that approximation is representable, has values which can be computed. There is a question, how do we achieve a cyclicity that is a little bit more complicated. So for that, we need to introduce a scaling vector. I am finishing, I think it's almost, I'm almost done. So the scaling vector is a integer positive coordinate vector with scaling isomorphism is just multiplying a vector coordinate-wise. So it's like a scalar product, but by an integer vector. And the scaling of a cubical set, X is X alpha is the image of that. The lambda alpha, this and this are isomorphisms, and they are, one can easily compute isomorphism induced in homology. That's easily computable. So the scaling of a map F would be F alpha given by inverse scaling composed with F. So we have a theorem saying that if xy are cubical and F is continuous, if alpha is big enough, then the smallest cubical graph enclosure of F alpha is acyclic valued. The formula that gives us the formula for the homology induced by a map. So we have a map F from X, Y. We have the scaling F alpha, the inverse scaling here. So F alpha is defined, this F alpha is by definition this composed with that. But then in homology, this is well-defined, computable. Easily computed. This is well-defined, computable. This commutative diagram induces this commutative diagram. So then we define this as the composition of those two maps in homology. That's the definition only. And with this, I think I have set up some basis which I can refer to in my next 2 lectures when it comes to using homology. So that's all what I wanted to say. Gracias.
Super. Thank you very much. So we have at least one question. I think I also have a question. So from Ellie Carbonen, we have a question: what are the weaknesses of cubical complexes compared to simplicial complexes? And I'll ask the reverse is what are the strengths as well.
Yes, this is a very good question. So you will see, I do not limit my study to cubical complexes. You will see. Maybe I should go to some slides. There are kind of applications where simplicial complexes are natural. So here, when we look at this, simplicial complexes come naturally from a problem. So I would not know how to use a cubical complex for that problem. When there are problems like in imaging, so that would be here where we compute. We have already, this is formulated as a grid. When we have a natural grid, data is given by a grid, then the cubical complex comes naturally. Now we have a problem that in terms of theory, that a cubical set can be we can find triangulations of a cubical set. So to express it as a simplicial complex, but we cannot find cubization, simple cubization, if I may so, of a polyhedron. So in our book, we do introduce topological polyhedra, and we say that every topological polyhedron, whether simplicial or not, can be expressed by certain isomorphism as a cubical set, but it's not evident. So the back thing about cubical set is that it is in our setting, the cubical grids, that it's rigid. So it's applied to cubical grids in spaces for data, for certain types of data. Yep. Okay. I don't hear. Oh.
Yeah. Okay.
Sorry, there was too much echo.
Yeah, there was a bit of noise. So
yeah. So maybe was there a question?
I don't think so.
No. Okay. Yeah. I thought it's somebody asking me a question.
No.
Oh.
And yes, I have a follow-up question to that. Are there computational advantages when you're computing homology to using cubical over simplicial complexes? Like in these reductions you did?
Okay. I have to say that at the time when we were designing that, that was some time ago, because the book was written in 2004, and there was I think that was where the fastest algorithm which could be used to compute things like, for example, this what you see here. Okay, if you wanted to do it other way, no way. But nowadays there is so much progress in computing homology that I would say the most efficient algorithms are actually based on Lefschetz complexes.
Okay.
Which are complexes. Lefschetz calls them complex. Lefschetz, what we call Lefschetz complex in a Lefschetz book is complex. So this is the complexes based on poset relation, and these are very algebraic structure. These are the best, the fastest computation. But there is a different question of computing homology induced by a continuous map. And here, when we want to have continuous maps on some spaces, topological spaces, then a question, how are they represented? So if we have topological spaces which are subsets of some cubical grids, then first the homology of a map was the first thing which was really practically computable in any dimension. And then the simplicial maps were computed before only for certain specific cases. So that's one thing. The other thing is that when the setting is in a grid, cubical grid, then that's the very efficient computation. So if we look at this picture here, then this one, then that the whole idea is in this picture, and this formula, there are formulas which enable very fast computation here.
And so
simplicial map is constructing simplicial map, and its homology is a kind of mess.
And so in particular, when if you're interested in these dynamical settings, right, the cubical complex is really what you want. Okay.
Yeah. Great. So it's I would say the structure, the complex should be chosen appropriately to what are we studying.
Great. Well, thanks a lot.